If you have not watched the previous video on the cycloalkanes, I would suggest that you do that before continuing on with this video, because we're going to talk about some stuff that I covered in that video. So at the end of that video, we were left with a bit of a tricky situation because we decided that the general formula for the homologous series of cycloalkanes was CnH2n. However, in a video before that, we decided that this was also the general formula for the alkenes. So, how are we to tell if this general formula is talking about an alkene or a cycloalkane? As I mentioned in the previous video, we will get to the chemical test that actually allows us to tell the difference between these two types of compound, because there is a chemical test that we can do to prove which one is which based on how they react with other chemicals. But for just now, we need to get to the bottom of this. Why is this allowed in chemistry? Why is this a thing? Because what we're left with in this situation is molecules, compounds that have the same atoms, the same number of carbons, the same number of hydrogens, but they're just arranged slightly differently. They have a different structure. And in chemistry, as I mentioned in the previous video, this happens all the time. This is a very common phenomenon. And the word that we use to describe pairs of compounds, pairs of molecules, sets of molecules that behave like this are called isomers. So what do we want to know about isomers? Well, first off, just to repeat myself here, alkenes and cycloalkanes follow the same general formula. That's the problem that we have. Okay, it's difficult to tell just on paper, in theory, if we have an alkene or a cycloalkane, because they follow the same general formula. They have the same, potentially exact same number of carbons and number of hydrogens. Okay, so if they have the same number of hydrogens and the same number of carbons, how are they different then? Because they have the exact same atoms. So what makes them different? Well, we already really know the answer to this because we have drawn out these compounds in detail. Okay, so for example, if I chose the area of this general formula that gave me 3 carbons and 6 hydrogens, this could mean this, because if I count through this, I can clearly see that I have 3 carbons, just like the molecular formula tells me to have, and I have 6 hydrogens, just like it tells me to have. And every carbon that I have has 4 lines, 4 bonds coming off of it, so it's allowed. And it's clearly an alkene because it has a double bond, it's unsaturated. So that would be a perfectly valid C3H6. However, we also know from the previous video that by using the same molecular formula, I could also have this cyclic hydrocarbon structure, this cycloalkane. So that molecular formula, that C3H6, is actually not very useful at all in telling me which exact compound I have. But more on that later. For just now, we want to define how these compounds relate to each other, because they are closely related, right? So what is similar about them and what is different about them? Well, if we just look at what we've got in front of us, we have 2 compounds and they have the same molecular formula, C3H6, but a different structural formula, which is shown by these full structural formulae. And that is why the full structural formula is so important, because it tells me all the details, all the different types of bonding that can be involved, exactly how the atoms bond to one another. Because the molecular formula does not tell me that, it just tells me the total number of atoms that I have. So, in defining an isomer then, we are talking about pairs of compounds or sets of compounds that have the same molecular formula, the same number of atoms of each element, but a different structural formula. The atoms and the bonds are arranged in a different way. And this actually brings us on to a couple of important questions. There's a few questions that we can now ask about isomers and how they arise, and what are the real differences between them, what are the similarities between them. But most importantly, I think, there are two key questions that we now need to answer. Do isomers react in the same ways? So for example, if I go back to my C3H6s, do they react in the same way? They have the same molecular formula. If I reacted them with other chemicals, would they do the same things? Would they behave differently? If they behave differently, why do they behave differently? And the second question would be, can we have isomers within one homologous series? Could I look at one homologous series, for example, the alkanes, and find isomers within that family? Or does it always have to be across two different sets of homologous series? These are the questions that we're going to answer in the next video.